the board?
Yes, sir.
Yes, sir.
Okay. So any questions or doubts regarding previous class?
Sir,
Hmm. So
in the
please
Sakura,
identify yourself and then go on. Then speak.
sir, Rishikesh,
Okay. Go on.
in the in the Sakura book, he had given the different approach for the Dirac equation. He takes two wave function of phi r and phi l and says that one is parallel to the.
No,
Yes,
not
sir.
one is not. One is what? One is what? One is parallel what? What are you talking?
One is parallel to the spin and one is anti-parallel to the spin. He says phi r and phi
No,
l.
no, 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 no. No. That will come later on. But first we have to consider the Dirac equation, right? It's not a. It's not a day. No one can derive Dirac equation as such. Okay. So it is just the way it arrived, the way it is guessed. That is what is pointed out. So this is we have also not derived the Dirac equation. But in that Shire will come later on. Any other question?
Sir, this gamma mu does not transform like a 4 vector.
We'll see how it transforms. We'll see how it transforms. It is a 4 vector, okay, but it is in the space of matrices. Okay. Okay, so let me recapitulate what we did in our previous class. Okay, we introduced a wave equation which is first order in T and first order in spatial derivatives. Okay, and demand the consistency with energy momentum relation. That force to okay, those anti-commutation relations, okay, together with the fact that together with the hermicity, okay, leads us to conclude that the minimum size of this matrix should be 4. Minimum size of those matrices should be 4. Okay, fine. Then we use those matrices and we have written down the covariant version of Dirac equation. Okay, so this is what we did. Okay, so there are certain properties of gamma matrices that you should there are certain properties of those 4 matrices that we should you should know. Okay, so namely this anti-commutation relation and tracelessness, etc. Okay, so while writing the Dirac equation in covariant form, okay, we introduced different version of those 4 matrices, which we'll call as gamma matrices. These are called gamma matrices. Okay, so gamma mu is gamma 0 is beta and gamma I is beta alpha. Okay, in the standard representation or in Dirac representation, okay, which is one of the bases in the space of matrices, okay, we choose certain representation for beta and alpha. Okay, namely beta equal to identity 0 0 minus identity, okay, and alpha is 0 sigma 0. Okay, so we know gamma mu in terms of those identities and sigma matrices. Okay, is this clear to all? Okay, so let me spell out explicitly the gamma 0 matrix. Okay. Gamma 0 matrix is beta. This is equal to identity 0, 0 minus identity. Okay. And gamma I is equal to beta I. Since me, the sign difference between sigma this in the in this entry of gamma compared to alpha. Okay, good. So this is your gamma I. Okay. Now you see that gamma square, since it is beta, is equal to identity. So it is a 4 cross 4 identity. Okay. But what about gamma I square? Gamma I square is beta alpha I into beta alpha I. Okay. You use the anti-commutation relation between alphas and beta. Okay, and take beta to the extreme left. Okay. Beta square will be 1. You left with minus, because of that anti-commutation relation you will get minus sign. Okay. So you will get minus beta square alpha I square. Okay, so beta square is identity and alpha square is also identity, so you will get minus identity. Okay, clear? Similarly, gamma 0 in this representation, gamma 0 in the standard representation, gamma 0 is Hermitian. Okay, so it is gamma 0 dagger is gamma 0, and gamma I dagger, okay, is beta alpha I dagger. Okay, beta alpha I dagger. So this will be alpha I dagger, beta dagger. Okay, is equal to this is minus beta alpha I, and that is equal to minus gamma I. Okay, therefore gamma I dagger is minus gamma I. In other words, these gamma I's are anti-Hermitian. Okay, and now you can see why we have not written the covariant direct equation in Hamiltonian form. We cannot write. Okay, but once we want to write in Hamiltonian form, then Hamiltonian should be Hermitian. Okay, but in the covariant way of writing the direct equation, what we have is the gamma matrices, and gamma i's are Hermitian, anti-Hermitian. Okay, but there is nothing wrong in it. Okay, we can always go back to this expression. Okay, we can always write this as h times psi. Okay. Similarly, now, what are the anti-commutation relations between gammas? Okay, so we have, you can easily show that gamma 0, gamma I, okay, using the definition of gamma in terms of beta and alpha, okay, and using the anti-commutation relation between alphas and betas, you can easily show that this is gamma 0, gamma I is 0, okay, and anti-commutation relation between gamma I, gamma j equal to, okay, minus 2 delta ij. And since these are matrices, 4 cross 4 matrices, I have to put identity. So you should not confuse between this and this. Okay, delta ij, these are the indices referred to the indices on gamma matrices, but they themselves are matrices. Okay, clear? So the matrix nature of gamma reflects in this identity, and this index nature of gamma reflects in this chronicle delta. Okay, clear? So somebody might ask, what is the alpha beta element of this anti-commutator? Then that is delta is an alpha beta element of this identity. Okay. So these are matrices, 4x4 matrices. So you can use the original definition of anti-commutator, gamma I gamma z plus gamma j gamma I, and you can explicitly find out the matrix, okay, that is this, and multiply them and take alpha beta element. Okay. So this index is different than this index. So please do not get confused with this. There is a high chance of confusion. Okay. Fine. So now we can combine this expression and this expression, and we can write gamma mu gamma nu as twice eta mu nu identity, where eta mu nu is diagonal of one your usual metric. There is nothing special about why metric is coming. We noted that eta 0 0 is 1, okay, and eta ij is minus delta ij. Okay, so this is just a way to write in a compact fashion these two expressions. Okay, fine. Similarly, now you can, given this gamma mu, okay, one can write gamma lower mu as eta mu nu gamma. Okay, so this you will see that this is indeed a 4 vector, but in place of matrices. It's not it is not usual 4 vector. Okay. Okay. So gamma lower 0 is gamma upper 0, that is equal to beta, and gamma lower I equal to minus gamma upper I. Okay, and where gamma upper I is given by this. Okay. Any question here so far? Any question? Okay, fine. So now let me go to next topic. So there are other interesting properties of these gamma matrices which will come to, okay, in maybe one day or two. So the Dirac equation in coherent form is given by, recall what is Dirac equation in coherent form? I cross gamma mu del mu, okay, minus MC acting on psi is equal to 0. Okay, so this is the matrix equation. Okay, so since these gammas are 4x4 matrix, here there is an identity which I am not writing. Okay, there is no point in writing identity always. Okay, so but it is understood that there is an identity here. So it is a 4x4. This is 4x4. So this should be 4x1. Okay. Yeah. Suppose I want to take the conjugate of this. Okay. Suppose I want to take the conjugate of this equation. How should I do? So that is what we will see now. Okay. So first of all, we have to define what is this psi. Psi is psi 1, psi 2, psi 3, psi 4. Again, note that these four components, occurrence of four components has nothing to do with the 4 vector. Don't say that this is a 4 vector, although it looks same. Okay, your 4 vector mu in column vector fashion, it is a0, a1, a2, a3, right? So this is not like this. Transformation property of this is completely different than this one. Okay, this is just a 4 component object, not necessarily a 4 vector. In fact, it is not the 4 vector. Okay, so these indices on gamma, which is mu, are Lorentz indices. Okay, mu are Lorentz indices. Okay, so they take care of the transformation property under Lorentz transformation. While if you want to expand this matrix equation in component form, you should have written I h cross gamma mu del mu minus identity MC. Okay, it's alpha beta element. Okay, then psi beta equal to 0. Okay, where alpha beta runs from 1, 2, 3, 4, not 0, 1, 2, 3. Okay, so these alpha betas are different, okay, than this mu nu. Okay, sometime I use alpha and beta as a Lorentz indices also, but I will when it happens, then I will point out that. Okay, but don't get confused with these indices. Okay, so this expression is same as this expression. Okay, so this is actually the 0 here is actually a column 0. Okay, so you can say that these are the internal indices. This is what is known as internal indices. Okay. 1, 2, 3, 4. They are not Lorentz invariants. I repeat, they are not. These 1, 2, 3, 4 are not the Lorentz indices. Okay, so you should not write psi 1 as lambda 1 to psi 2. This lambda 1 mu psi mu is incorrect. It has no meaning. Okay, I hope it is clear. Now, once we have this 4 component object, we can define its dagger. In general, these entries psi 1, psi 2, psi 3 are common functions of psi 1 star, psi 2 star, psi 3 star, and psi 4 star. Okay, clear? Okay. So now I want to construct a conjugate equation of this Dirac equation, conjugate of this Dirac equation. Okay, so it is at the since we are at the beginning level. Okay, let me write, instead of this covariant equation, let me go back to our main equation. Okay, so that is I h cross d psi by dt, okay, plus I h cross c. Okay, instead of p, I will write gradient. Okay, psi minus mc square beta psi equal to 0. Okay, so this is your Dirac equation. Okay, now I will take the conjugate of Hermitian conjugate of this. what I will get? I will get minus I H cross T psi dagger by del T, okay, minus I H cross C. Okay, what will happen if I take the Hermitian conjugate of this? This gradient of psi will come first and alpha will go later, and there will be dagger. Okay, so this will be dagger, okay, dotted with alpha dagger, okay, minus MC square beta dagger psi dagger beta dagger. Okay, psi dagger beta equal to 0. Okay, fine. Now what I will do, I will multiply. Okay, okay, so okay, what I will do, I will construct a quantity called psi bar. I will define a quantity called psi bar, which is equal to, just for a convenience, and we will see later how this is useful, psi dagger beta, that is same as psi dagger gamma 0. Note the order. Okay, now you see the ordering between beta and psi's are important. Okay, I cannot arbitrarily place this alpha here and psi here. Okay, one has to be careful because this is column, this is 4 cross 4. So one has to be careful in placement. Okay, I will define this quantity. And what I will do, I will write this expression in terms of psi bar. Okay, so this is it. So this is your conjugate equation. So you can use the Hermitian property of betas and alpha. So this will be beta psi dagger beta. This will be gradient of psi dagger alpha, and this will be psi dagger. Okay, yeah. But I want to rewrite this expression slightly differently. So I will write this as minus I H cross del psi dagger del T. Okay, and I will write here, since gamma 0 square is 1, okay, I will insert gamma 0 square here, that is identity, right? Okay, and one of the gamma 0 will go, so one of the gamma 0 will attach with the psi dagger and makes it psi bar. Okay, so ultimately what I will get here, I will get psi del T of psi bar gamma 0. Okay, that is your first term. Okay, minus I H cross E, okay, gradient of psi, okay, gradient of psi dagger is gradient psi dagger. Okay, now gradient psi dagger, okay, again I will introduce here gamma 0 square. Okay, so this will be gradient of psi bar, gradient of psi bar. Okay, that is one gamma 0 has gone, and another next gamma 0 will attach with this vector alpha, because alpha, vector alpha beta will attach with this vector alpha from the left and makes it vector gamma. Okay, so this will be this. Okay, minus MC square. Okay, now here we don't have to do anything, so this is just psi equal to 0. Okay, right? So this I can write. Okay, so I will, so it will be I H cross. So this will be I H cross. Okay. Now I can write it in a coherent fashion, del mu psi bar, okay, gamma mu, okay, plus MC psi bar. Okay, equal to 0. So the same expression I am writing in just a covariant fashion. Okay, minus sign I have taken common. Okay, so del t becomes c times. Okay, so there is a c here, but that c gets cancels with this c square. Okay, so I can write this as c times del 0 psi bar gamma 0 plus I h cross c times del I psi bar, okay, gamma I, okay, plus mc square mc psi bar, okay, mc square psi bar. So c cancels, okay, and you will get this expression. Okay. This I can write, okay, in the following way. Okay, there is you can use this, okay, but this I can write in slightly convenient form. Psi bar, I will write psi bar first, okay, then but they will act from the left now. Okay, the meaning of this arrow is that del mu will act on this psi bar from the left. Okay, and you have to put it here. Okay, so this will be plus mc equal to 0. Okay, so meaning of this arrow is that this psi bar gamma mu del mu is nothing but del mu psi bar, okay, gamma. Okay, why I'm doing this? Because see, I cannot take this psi bar through gamma. Okay, so I cannot write this operator acting on psi bar. That I cannot do. Okay, so if you want to write as some operator acting on psi bar, you have to write in this way. So this operator, this entire operator, will act from the left on psi bar. Okay, so this is your either this or this is your covariant form of conjugate Dirac equation. Okay, clear? So we'll come to this psi bar later on again. Okay, but note this definition. Now let us use this expression. Sometime I will use this expression, sometime I will use covariant equation. Okay, whichever is convenient. Okay, both are the same. So let me rewrite this conjugate equation, okay, in non-covariant form. Okay, so this will be your IH cross. It will be, you have Dirac equation IH cross del. First I will write the Dirac again. Okay. Sorry. Okay. Minus mc square beta psi equal to 0, and its conjugate equation will be IH cross del psi dagger by del t, okay, plus IH cross c, okay, gradient of psi dagger dotted with alpha, minus mc square psi dagger beta. This equal to 0. Okay, so now you construct Shai dagger of Dirac equation, okay, minus Dirac equation dagger Shai. Okay, so you construct this quantity. Okay, this will be 0 because on the right hand side it is 0. So let us multiply from the left of this direct equation and then subtract from it this while by multiplying from the right by Shai. That is what this quantity is. Okay, so you will get IH cross, okay, Shai dagger del Shai by del T. Okay, this is coming from this. Then I will subtract from this quantity. Okay, subtract from it. Okay, so
There is minus sign, I think, in the second equation.
wait. So it's a dagger here. So no, there is no minus sign. Minus sign I have cancelled everywhere. There is a minus. That I have cancelled everywhere. Okay, so that is 0. So subtract from it. I is cross. No, I wanted to write in slightly different form. This is correct. This is correct. So I have to subtract it. This subtraction is the sign problem. So I cross Psi dagger del Psi del T. That is system. And minus here. Now there should be, if it is I'm writing minus here, that should be plus, right? If I take minus through, then this will be plus. Yeah. Okay. Fine. Now in this form you add it. Okay. You add, since I have taken minus sign common, I could have kept this minus sign. Okay. But in this form you just add them. Okay. You multiply from the left Psi dagger to Dirac equation. Add to that this conjugate equation after multiplying with Psi from the right. Okay. So if you do that, you will get IH cross del Psi dagger by del T. Okay. Psi. Okay. Plus IH cross C. Okay. Alpha dot plus Psi dagger. So there will be Psi dagger here. Okay. Plus gradient of Psi dagger dotted with alpha. Okay. Psi. Okay. And this term will cancel. Okay. Fine. So this I can write as del T. Okay. So IH cross I can cancel. Del T of Psi dagger Psi. These two terms I can write as del T of Psi dagger Psi. Okay. Plus this term I can write as C times, okay, this gradient, okay, so this will become del dot, okay, psi dagger alpha psi, okay, this is equal to 0. Okay. Now you can bring this C here, okay, you can bring this C here, okay, and write as let me insert one more step here. Okay. So this I can write as okay. So let me define first row, which is psi dagger psi, and I will define three vector J by psi dagger alpha psi. Okay. So this equation tells us that del rho by del T, okay, plus T times, okay, C is there, so I don't have to write C. Del dot J equal to 0. And this is nothing but your continuity equation. Okay, so rho is our charge density and J is the current density. We'll come to this expression again, okay, but let me write this entire thing in a coherent form. So I can insert here gamma 0 square. Okay, so one gamma 0 will attach to psi dagger and makes it psi bar. Okay, and one gamma 0 remains in between psi bar and psi. Okay, similarly, I can insert gamma 0 square here. One gamma 0 will attach to psi dagger, makes it psi bar, and one gamma 0 will attach to alpha vector alpha and makes it vector gamma. Okay, so and then I will divide it by C. Okay, that will make this as del x0. Okay, so I can write this expression as del mu. Okay, I can write in a combined way. I can write this as del mu psi bar gamma mu psi equal to 0. Okay, where J mu. So now I will, this is equal to del mu J mu, where J mu is J0 and J, okay, which is nothing but P times rho and J. Okay, right? And explicitly in terms of this thing, your J mu is psi bar gamma mu psi. Okay, right? Here, coherent. You see, this is the coherent. Del mu of 4 vector J mu. Okay. Now you see the expression for rho is psi bar, psi dagger, psi, or you can write this as, or it is psi bar gamma 0 psi. This quantity is what? This quantity, if you evaluate explicitly, take any psi. Okay. So this will be psi 1 star, psi 2 star, psi 3 star, psi 4 star. Okay. And this will be psi 1, psi 2, psi 3, psi 4. Okay. So this will be mod of psi 1 square, psi 2 square, psi 3 square, etc. Okay. Hence, this will be positive definite quantity. Hmm? Okay. So your rho is positive definite. So the first problem is disappeared now, which was occurring for Klein-Gordon equation. And you can trace back the reason why we were able to solve this, because we converted the second order differential equation into first order differential equation. Okay. But then the price we have to pay is that we are increasing the components. Now there is not a single psi. Okay. In Klein-Gordon, we have just single entity phi or psi wave function. Now I have this wave function become 4 component object. Okay. The degrees of freedom have increased now. Your internal degrees of freedom have increased now. Okay. Previously we were dealing with only one entry called phi or psi. Okay. Now instead of that we have 4 degrees of freedom. Psi 1, psi 2, psi 3, psi 4. Okay. So while we solve the problem occurring with probability density, okay, which was negative in the Klein-Gordon case, okay, we have to deal with this 4 component object. Okay, and later on you will see that this 4 component object, okay, represents, okay, positive negative energy solution with spin up and spin down. Okay, this encodes positive as well as negative energy solution with spin up and spin down. So this 4 component object will be positive energy, okay, this will be negative energy, okay, and these individually will represent spin up, spin down. There is also spin up, spin down. Whether which one to call positive, which one to call negative, we'll see. Okay. So automatically this spin is occurring. One can sense that. Okay. But we have to wait for some time. Okay. Clear? We'll come to this later. Okay. It's not that simple. Okay, fine. So now, while seeing this form, okay, after seeing this expression for rho or current three current density, okay, okay, 3 current density is this, okay. You could have guessed that this C times alpha is something like, see, in your classical physics, how you write the current density, okay, in your classical mechanics, how you write this current density or charge current density in that case. Charge current density is E times V, right? Okay, charge E times V, or maybe I should write Q times V. Okay, agree? Okay. What we are getting, our 3 current density is C psi dagger gamma I psi. No, there is no C. I should write alpha. If I want to write C here, then I should write alpha here. This is our expression for this current density. Okay. And what is our rho? Rho is psi dagger psi. So here also I should write here. I should write here dagger. I should write here dagger instead of this bar. I should write dagger. psi dagger, C psi dagger, alpha I psi, and our rho was psi dagger psi. Okay. If I interpret this as a charge, density, okay, then what is happening here? Okay, this is what single charge particle. Okay, if I have density, then it will be rho times V. Okay, then this is the current. Okay, current density will be charge per unit volume, so it will be charge density V. Okay, so this is like your C alpha is coming in between. So, but vaguely, I'm not writing it correctly. Okay, so vaguely this should be C alpha rho kind of thing. Okay. So if you compare naive comparison with this our classical expression suggests that this quantity C times alpha is some kind of velocity. Just naive comparison. It's just some kind of velocity, C times alpha. Okay. Let us in your usual quantum mechanics, you are aware of Heisenberg picture. Okay. What is the equation of motion in the Heisenberg picture? Equation of motion of certain operator. dA by dt is equal to what? I by h cross h with a, okay, minus del a by del t. Okay. If it is not explicitly dependent on time, then this quantity will go. Okay. Now let us apply the same procedure here. Okay. Let me write the position. Consider the position operator. Okay, in our in Dirac theory. Okay. And I am saying that this position operator is defined in Heisenberg picture. Okay. I am not going into the details. Okay, but this is in the Heisenberg picture. This operator. That means it will have what is your Heisenberg picture? Heisenberg picture operator will be e to the power minus I h t by h cross. Okay. Schrodinger picture operator R Schrodinger and e to the power I h t by h cross, something like this. Okay. There might be this plus and minus may be occurring in different positions. Okay. But let us consider this position operator in Dirac theory. Okay. And let us construct the time evolution of that dr by dt. What will be that? This will be I by h cross, okay, h with r, and it does not depend on time explicitly, hence this term will not be there. Okay, but what is h in our Dirac theory? H is, go back to our first equation. Okay, in this this will be alpha dot p, okay, plus beta mc square. This was our Hamiltonian, Dirac Hamiltonian. So what is this? So this will be I by h cross c alpha dot t, okay, plus beta mc square and commutator with r. Okay. Note that this, as far as this commutation relation is concerned, okay, the commutation relation between p and r matter. Okay, these are the alphas and betas lie in different space. They are not in your coordinate, not in your physical space. Okay. Okay. So when I write r here, it is understood that there is an identity. Okay. So this refers to these alphas and betas. Okay. And r and t's are your they represent operators in your space, in your Minkowski space. Okay, in real space. So what is this commutation relation? So this will be, okay, you demand the usual commutation relation between x and p. Okay. So with that, okay, what you will get is, okay, so this will be I by h cross and r. Okay, so you can write pi xi. Okay, so you can write this as alpha I pi, okay, commutated with ri. Okay, so you'll get, what you will get is c times, okay, alpha, that's it, c times alpha I, it will be vector alpha. This will be the commutation relation. So this is equal to minus minus, so it will be equal to c alpha. Indeed, you can see if I say this as some kind of velocity operator, then this will be c times alpha. Okay, and this matches with our expectation, but one should not extrapolate too much this velocity operator, in the sense that this will not represent some kind of velocity of a Dirac particle or something. Okay, it's just a Heisenberg equation of motion for R. Okay, see, what is the point is that, okay, since we are discussing relativistic free particle, okay, we are discussing the relativistic free particle, okay, this v must be constant. Okay, but if I take, suppose if I take dv by dt, suppose if I write the equation of motion for this v operator, what will be that? That will be I by h cross, okay, h with v operator. Okay, this is not equal to 0. You can check, you can follow the same procedure and calculate commutation of h with v operator. V operator is c alpha. Okay, that is not equal to 0. So there is no such a meaning that can be given to this v operator. Okay, yeah, it's just a aside. Okay, you apply, you consider in Heisenberg picture, you consider the equation of motion for R that turns out to be C alpha, which was sitting in the expression for this current density, C times alpha. So vaguely, this is like, that's why we say that this is a three current density. It is charge density into velocity kind of thing. But don't extrapolate too much on this, because the velocity has so just, but anyway, you just calculate this bracket. Okay. What about dp by dt? Okay. dp by dt. What about this? Okay. This will be IH cross I by H cross H with P, right? Okay. But you see, H is what? I by H cross commutation with C alpha dot P. Okay. plus beta mc square p. Okay, this operator commutes with this. This operator commutes with this. Okay. This is 0. Is it clear? Okay. So dp by dt is 0. So p is constant of motion. Okay. What else do you expect? You have a free direct particle. You have a free relativistic particle. What do you expect? What else would be the constant of motion?
Total energy.
That is there, right? See, E is there. E is already there. E we are assuming. So E is P square, C square plus M square C to the power 4. Apart from this, if
Angular
E is
momentum.
a constant of motion, then E will be constant of motion. Okay, let us see about the angular momentum. So let us define the angular momentum in usual way. It is R cross P. And let us see what happens. Okay. So dl by dt. Remember, we are in the Heisenberg picture. dl by dt will be I by h cross h with L. Okay. So let us calculate. So this boils down to calculation of this commutator h with L. Okay. What is this? So this will be P alpha dot P plus beta mc square, okay, with L. So this is L is your R cross P. And remember, there is an identity always sitting, okay, beside all your usual differential operators, usual operators, differential or other one. Okay, fine. So this operator will commute with beta because beta will have identity. All this and with this C alpha dot P, okay, and R cross P. Okay, so this is nothing but, okay, what C, okay, there is an identity here. Okay, alpha will always commute with identity. So as far as this commutation between alphas and this alphas with identity is concerned, it is 0. But there is a non-trivial commutation relation between P and R, and there is a cross product. Okay, so this will be C alpha dot P, okay, commutation with R cross P, right? Okay, so this is understood to be R cross P. Okay, so this will be what? Okay, so this will be P R commutation relation, that is minus I H cross. Okay, so it will be minus C minus I C H cross, okay, and alpha cross P. Okay, so this will be I H cross C P cross alpha. Okay, now you see this is not 0. Okay, so why we demand that this angular momentum should be constant of motion? Because free particle, relativistic or otherwise, free particle is is not acted upon any potential, and hence there is an isotropy of the space, and hence there is a rotational invariance. Under rotational invariance, the generator of rotational invariance is angular momentum. Generator of rotation is angular momentum. Okay, that should be the constant of motion. Okay, so rotational invariance is essential in demanding the conservation of angular momentum. Okay, so we have here rotational invariance. We have free particle. There is no potential at all. But still, this angular momentum is not constant. Okay, it would be constant if we add some part to it, such that this term goes away. Let us see. Okay, so this part, I will write the expression. Okay, I will keep. Okay, so I will complete this first. Okay, so this will be so IH cross so dl by dt will be IH cross, okay, into this, so I plus, so it will be C times alpha cross P. Okay. Right. So now this is not constant of motion. So can I add to this L some part so that that remaining part will cancel this term? Okay. But that part should not depend on your coordinates, because again see, here we are using the definition of angular momentum. Okay, so this is R cross P. There are coordinates which are occurring here, your real coordinates R and P. Okay. If I want to add something here, that should not involve coordinate. Okay, otherwise again I can absorb that here. That will not work. Okay, I want some, see here which commutation relation played a role. Okay, commutation relation between P and R. Now I want something wherein this commutation relation of alpha plays a role. Okay, let us see. Suppose if I say that this is the quantity, so suppose if I construct some quantity, say A. Okay, A will be, say, so we have the way we define gamma I is 0 sigma I minus sigma I 0. Okay, this is our gamma I. Gamma 0 will be identity 0 0 minus identity. Okay, now suppose if I define this A in this way, okay, sigma I 0 sigma I, and I will do half here. Just let us consider this quantity. What is going to happen? Suppose if I take the commutator of H with A. Okay, what is going to happen? It will be C alpha dot P, okay, plus beta MC square A. Okay, and there is a A is this, okay, beta is at 1 0 0 minus 1. Okay, it's diagonal completely. Okay, so this will commute with this. There is no problem at all. Okay, so this will be C alpha dot P, okay, commutator with A. Okay. What is this commutator? So this will be C. Okay, so let me write it explicitly. So this will be commutator of alpha dot P with sigma I, sigma, so this A will be not. If I write I here, then I have to write AI. So let me write here. So it will be 0, 0. Okay. So we have 4 cross 4 matrix. It's commutator with this 4 cross 4 matrix. Okay. Okay. These are 2 cross 2. All these are 2 cross 2. Okay. So what is this? This will be the yeah. But now what is alpha? Let us substitute for alpha. What is alpha? Alpha is 0, okay, dot p sigma dot p and 0, and its commutator with sigma 0, 0, sigma. Okay. So what is this? This is C times commutator. So see, this is, since it is in the block form. Okay, what will be this commutator? Commutator of this matrix with this matrix. It will be a matrix with 0, commutator of sigma dot t with sigma, commutator of sigma dot t with sigma, and 0. Agree? Okay. It is a block diagonal. Okay. You have blocks here. Okay. Commutator with another matrix which is also in the block diagonal. Okay. So this commutator with this commutator with this, okay, and so on. But these are zeros here. So there is a even more simplification. Okay. So that's why it is just, you can explicitly show this. Okay. You take this into this minus this into this. Okay. And you can rearrange it in this form. Okay. So what remains is the calculation of commutator sigma dot t with sigma. So it boils down to commutation relation between 2 cross 2 poly matrices. Okay. So let us see what is that. Okay. So sigma dot t with sigma. Okay. Okay. So this will be, since this is a vector, okay, so it will have some indices, right? Okay. Let us say that we are looking at ith commutator of this, or jth, so jth commutator of this. Okay. So this will be sigma dot p with sigma z. Jth commutator. So there will be 3 poly matrices, and here we have to take commutation of those 3 poly matrices with this sigma dot p. Okay. So sigma dot p commutator with sigma 1, sigma dot p commutator with sigma 2, and sigma dot p commutator with sigma 3. So let us say that we want jth commutator. Okay, that is sigma z. What is this? Is there, okay, and sigma z. Okay, but pi does not belong to this space at all. Okay, so this is equal to pi, okay, commutator of sigma I, sigma z. What is commutator of sigma I, sigma z? You tell me now. I asked you to go through this polyspin matrices. I gave you the reference also. So what is this commutation relation?
Epsilon ij k I h cut sigma k.
Is 2i. Okay, so it will be this sigma I commutation relation. Okay,
So 2i epsilon ijk
ijk sigma k, right?
sigma.
Okay. So this I will substitute here. So what I will get? Okay. So sigma dot p, okay, its this thing will be 2I, okay, there will be pi, this I is complex I, okay, pi, okay, sigma I sigma j, that is epsilon I j k, okay, sigma k, okay. So this is equal to 2I epsilon I j k pi sigma k, okay, but this is nothing but using the property of Levi-Civita, 2I, okay, minus epsilon j I k pi sigma k, okay, clear? Okay, so this component of this commutator is this. So what will be for general sigma vector, okay, sigma dot p with sigma, okay, will be what? Okay, it is like, you see, epsilon I j I k pi sigma k, okay, what will be that? Okay, it is like p cross sigma, understand? Okay, so this will be minus 2I p cross sigma, where I used a cross b as epsilon I j k, its ith component is epsilon k, jth component of this is turning out to be epsilon j I k pi sigma k. Okay, so replace j by I by j, k remain as it is. Okay, so we'll get this. Okay, so sigma dot p commutator with sigma is minus 2I p cross sigma. Okay, so that means this matrix will become, this matrix will be, so what we are calculating, H with A, right? So this will be C, okay, C, sorry, A was half was there, right? So there is half will come everywhere. Okay, so remember there is a half. Okay? So there is a half. Okay. It's a half. Then there will be 0 minus 2I p cross sigma. Okay. Then minus 2I p cross sigma, and then 0 here. Okay, so this half will go, and this will be just C. Okay, so it is minus, so I can write this as minus C. Okay, I, okay, there is an I here, 2 will go with this 2, and I will write this P cross, and this will be 0 sigma 0. Okay, so this is nothing but minus I C P cross, what is this? This is your alpha. So this is alpha. Okay, so H commutator with A is minus I C P cross alpha. Okay, now I will give A, so I will multiply A by H cross here. Okay, so if I multiply by H cross, then there will be H cross here. Then there will be H cross here. Okay, there will be H cross. So there will be H cross here, and so there will be H cross. So H with A is minus I H cross C, okay, P cross alpha. Okay, So you see now H commutator with L plus A is what? Okay, H commutator L was H commutator L. H commutator L was IH cross C P cross alpha. Okay. P cross alpha. Hence it is. Okay. So if I add this part, okay, if I add this part, okay, to L, I get, and if I define that as my angular momentum, total angular momentum, okay, then that is constant of motion. And this part is interpreted as spin angular momentum. Now you see, Dirac theory, I have not done anything. I just took the commutation relation with H, between H with L. Okay, and I have seen, I showed that that commutation relation is non-zero. So Dirac theory requires some extra angular momentum. You see, there is a relativistic free particle. Okay, I have rotational invariance, so I expect the angular momentum to be constant of motion. But when I calculate commutation relation of H with L, I am getting non-zero result. That means this L is incomplete. I must add something to L so that H with that total thing is zero. That something is turning out to be this matrix. So this is a rough justification of how the spin is coming into the Dirac theory. It's automatic, it's there already. Once you write down this Hamiltonian, it is there. The spin is already there. Okay, so your angular momentum and spin angular momentum, they do not conserve simultaneously, individually. Okay, total angular momentum is conserved, or it is a constant of motion. So this is how the Dirac theory incorporates the spin. Okay, but this is very, very vague. What should I say? This rough or is very ad hoc way of understanding the spin. Okay, but it is coming. Now we are sure that the spin is there in the Dirac theory. This tells you that there is, in H there is a spin already sitting. Okay. One can approach this problem from the group theory now. Okay, and one can see that group theory also gives you the same expression. That will be a much more rigorous way of understanding this. This quantity, which should cancel this quantity. Okay. Okay, and it is clear why this thing is 4 cross 4. Okay, this now I will write, instead of A, I will write S. Instead of A, I will just write S. Okay, so this is my spin angular momentum. Okay, it is clear why this is happening in 4 cross 4 form. In your non-relativistic case, you define spin as h cross by 2 sigma, right? It is 2 cross 2. So your quantum mechanical Hilbert space was plus state and minus state. Okay, plus corresponds to h cross by 2 eigenvalue and minus corresponds to minus h cross by 2 eigenvalue. Okay, now here I have two copies of sigma, okay, placed in diagonal form, block diagonal form. Okay. This indicates that there will be four components. Okay, spin up, spin down for positive energy and spin up, spin down for negative energy. So both your positive energy as well as negative energy solution will accompany by spin up and spin down parts. Okay. Further, this addition of S to L is not ad hoc. Okay, this addition of S to L, so we define this total angular momentum J, which is L plus S. This addition, this is not ad hoc. Okay, we have a clear guiding principle what to add. Okay, this. Okay, so I have free Hamiltonian. Okay, I demand the rotation invariance. Rotation invariance is there. Okay, therefore I should claim the conservation of angular momentum, but it is not happening. Okay, the angular momentum is not constant of motion. The moment I add this part to L, okay, then the total angular momentum is constant of motion. So it's not an ad hoc addition, it is requirement of the theory. It is a requirement from the rotation invariance. Okay. But on the other hand, in your non-relativistic case, okay, you add this spin ad hocly. Okay. There is no mention. What is your Hamiltonian? Minus, in the non-relativistic case, it is minus Laplacian square plus V of x. There is no spin, nothing. Right? So your Schrodinger equation does not bother about spin. Okay? What you do is you add the spin ad hocly, and then you say my total wave function psi of x is spin part, and the total wave function psi xs is the spin part and coordinate part. What you do. In all this expectation value and so on. But here it's not the case. Here it is coming as a requirement in the theory. As a requirement of the theory. Okay. So you see how the principle of relativity is so crucial. Okay. Fine. So so this is not the still it's not a complete picture in the sense that one has to give some proper reasoning about this S, and one has to further investigate properties of S, how it is coming actually. Okay. So for that, one requires clear understanding of transformation, how Shai transform, how this four component object transform, etc. under Lorentz transformation. So one has to now one should go back to Lorentz transformation, study it in more detail. Okay. Now one has to study the generators of Lorentz transformation and so on. Those generators will give you the boost transformation and rotations. Okay, so one has to study that properly, and we will do that. Okay, not now, but maybe I don't know how when your exam is, I don't know, but even if it is not done in this semester, surely we are going to do this in next semester. Okay, but it is clear that the Dirac theory contains a more degree of freedom than what one should expect, and that extra degree of freedom is spin. So I will stop here, and then in the next class we are going to discuss plane wave solutions of Dirac equation and other properties. So if you have any question, you can ask.